Dear colleagues, my name is Zhezherya. I am from the Institute of Hydrobiology, National Academy of Science of the Ukraine, and Ukrainian Hydrometeorological Institute of the State Emergency Service of Ukraine and National Academy of Science of Ukraine. The topic of our presentation is dissolved carbohydrates as important ligands in metal complexation in the Ukrainian surface water. The aim of our research was to study the participation of dissolved carbohydrates in the formation of complexes with metals in various surface water bodies of Ukraine, as well as to analyze the seasonal changes and molecular weight distribution. As is well known, humic substances play the primary role in binding metal ions into complexes in surface water, since they are the most widespread group of dissolved organic matter. However, there is growing evidence that other components of dissolved organic matter, particularly carbohydrates, can also participate in complexation processes. This is especially true for water body with higher trophicity and intensive algae blooms. The carbohydrates concentration are high and humic substances are relatively low. A number of review articles have addressed this problem, show the extracellular polymer substances produced by algae, plants, and microorganisms are an important source of such carbohydrates. Extracellular polymeric substances are complex mixtures of polymers including carbohydrates, proteins, lipids, and nucleic acid. Among them, carbohydrates, polymers, mainly polysaccharides, make up the dominant fraction and play a significant role in metal binding. These polysaccharides are long chains of monosaccharides with many reactive groups such as hydroxyl, carboxyl, sulfate, and amino groups. These groups can interact with the metal ions, forming stable complexes, particularly with positive charged metals like copper, nickel, or zinc. For example, the binding of metal ions into complexes by chitosan macromolecules occurs with the participate of amino and hydroxyl function group, figure 1. In addition to the biological function, polysaccharides are widely used in environmental technologies as natural adsorbent for the removal of heavy metals from wastewater, for example, in materials based on chitosan or alginate. Carbohydrates metal complexes have practical applications. They are even used in medical and pharmacological purposes, for example, in anti-cancer therapies. Therefore, carbohydrates are not just structural components but active participants in metal complexes processes, influencing metal mobility, bioavailability, and toxicity in aquatic system. The aim figure The aim of our study was to evaluate, based on long-term research from 1995 to 2021, the role of organic substances of the natural fraction, mainly carbohydrates, in binding various metal ions such as iron, aluminium, copper, zinc, lead, manganese, vanadium, cadmium, and chromium in different types of surface water across Ukraine. The ability of carbohydrates to bind metal arises from the presence of electronegative function groups such as hydroxyl, carboxyl, and amino groups. For instance, chitosan, a common polysaccharide, bind metal ions from its amino and hydroxyl groups, forming stable complexes. The stability of metal carbohydrate complexes varies depending on the type of metal ion and the structure of the carbohydrates. Iron, nickel, copper, and vanadium complexes are particularly stable. Interestingly, some carbohydrates leads can prevent the precipitation of poorly soluble metal hydroxide such as iron, manganese. The significant role carbohydrates can play in controlling metal mobility in aqueous environments. It is also important to note that complexation can occur via different mechanisms, including outer sphere and inner sphere complexes. The specific mechanism depends on both the metal ions and the functional groups available on the carbohydrates. Here is a simplified over to the overview of the conditional stability constants of metal complexes with different organic ligands. As you can see, metals like copper, iron, and nickel form complexes of very different stability depend on the source of organic matter. For example, copper forms moderate complexes with extractory products of Daphne, logarithm constanta conditional 8.6, but much strong complexes with bacterial extracellular polymer uh, 15, 16, or cyanobacterial extrapolymer ferrum complexes with the algae Emiliania Huxley are extremely stable up to 21. These stable highlight the diversity of metal binding capacities of natural organic ligands in surface water. Table 2 presents the concentration of metal associated with the natural fraction of dissolved organic matter in surface waters of Ukraine. As we can see, these concentrations vary in a very wide range from trace amount to hundreds of micrograms per liter, depending on the element and the sampling site. Iron, for instance, range from trace level up to 262, while manganese may reach 285. Copper and zinc concentration in this fraction are typically below 40 microgram per liter, while cadmium and vanadium occur in low concentration. If we compare the relative proportion of metal associated with natural complexes, it becomes clear that these forms make up a significant share of the total dissolved metal pool. For example, from 32 to 56 on average percent of total dissolved iron and up to 45 dissolved copper are bound with natural organic complexes. 45. The highest proportions of metal natural organic complexes are found in smaller, more productive water bodies where algae activity is high, but humic substances are relatively low. Table 2 illustrates that is highly productive water bodies, small eutrophic lake and pond, the concentration and portion of metal bound in natural carbohydrate type complexes are substantially higher than in large rivers and reservoirs. You can see this and this. As we can see from the figure of slide 5 and 6, the relative content of the studied metal in natural complex with carbohydrate is higher in small water bodies, which often have higher productivity and this indicates that in this water, which often have higher productivity at relative low concentration of humic substance, a significant fraction of metal is bound to carbohydrate ligands. In other words, the role of carbohydrates in metal complexation become particularly important in such environments. The highest proportion of metal neutral organic complexes are found in small, more productive water bodies where algae activity is high, but humic substances are relatively low. The concentration and proportion of natural metal complexes in highly productive water bodies are significantly higher for copper, chromium, zinc, manganese, and iron compared to large reservoirs and rivers. This reflects the more intensive metabolic activity of phytoplankton and bacteria and the predominance of natural carbohydrate type ligands in such system. Particularly notable is manganese, whose natural complex concentration increase but more than an order of magnitude in small eutrophic lakes and ponds. This suggests that organic ligands such as carbohydrates and other algae metabolites may play a dominant role in metal complexation under such conditions. The molecular weight of metal carbohydrate complexes in surface water is highly variable, range from very low molecular weight fraction, often of microbial origin, to high molecular weight fraction mainly from terrestrial source. This broad distribution reflects the diverse composition of dissolved organic matter that bind metals. In Ukrainian water bodies, the molecular weight of these natural metal complexes vary from less than 1 kilodalton to over 70 kilodalton. This shows that both high and low molecular weight carbohydrates participate in metal complexation. During the year, the contribution of different fractions changes. High molecular weight compounds degrade into small molecular, which are actively utilized by organisms. The molecular weight distribution of copper carbohydrate complexes in the oblong bay of the Kanyev reservoir, figure 5. Varies seasonally. Both high and low molecular weight carbohydrate participate in metal complexation. Notably, the proportion of low molecular weight copper complexation less 1 kilodalton increased from winter to summer. Reflecting seasonal degradation of higher molecular weight compounds and enhanced biologic activity in the water body. Fraction of carbohydrates, this metal composition with a molecular weight less 5 kilodaltons are specific interest because they are potentially bioavailable for aquatic organisms. We found that the relative content of this low molecular fraction decreases in summer, especially in the oblong bay of the Kanyev reservoir and to a less extent in the Hryhvatsky pond in Kiev. This may seem unexpected since polysaccharides are more actively degraded in summer. However, these small molecules are quickly assimilated by biota, algae, and microorganisms during their peak growth. A similar pattern was observed for iron carbohydrate complexes, which are also had the lowest content in summer. For copper and aluminum, the seasonal trends were different and not directly correct with carbohydrates fraction. In particular, aluminum complexes will dominate in winter or spring, which likely reflects that aluminum is not essential for aquatic lives and therefore behaves differently. Conclusion: carbohydrates are, as a key component of dissolved organic matter, play an essential role in metal migration and detoxification in surface water. By forming stable complexes with metals, they influence both metals bioavailability and toxicity. The proportion of metals bound in neutral carbohydrate complexes vary by metal type, water body, and organic matter composition, being lowest in humic-rich water and highest in eutrophic bloom prone system. The molecular weight of these complexes range widely, less 1 kilodalton to 70 kilodalton, and changes seasonally, reflecting the transformation of how molecular carbohydrates into smaller, more bioavailable form. Complexes less 5 kilodalton are particularly important due to their higher biological accessibility. Practical metal carbohydrate complexes reduce heavy metal toxicity and enhance biological activity, suggesting their potential use in water purification and medicine. Therefore, continued research into these natural organic compounds is most significantly valuable and of growing practical importance. Thank you for your attention. If you have any question, write to email in this slide.